Hi, good evening. Please confirm if I'm audible or not.
Yes, sir, you are audible.
Okay. So I hope that you have gone through last week's, live sessions and also the lecture videos. So we'll be discussing a few theoretical questions based on the last few lectures. I have not included the part programming questions in this particular discussion. So if you have got any doubts pertaining to that, you can write it on the portal. And yeah, if you have any other questions, we can take them up and discuss towards the end of the session. So we have seen that in the last couple of lectures, Professor has discussed about different types of control strategies in CNC control machines. He has discussed about adaptive control systems, and you have two different strategies like control optimization and control constant. So I hope that you have gone through them. So coming to a few basic questions, in a stepper motor, the CNC based control loop that is used is closed loop control or open loop control or a combination of both or a feedback control system. So what will be your answer to this for a stepper motor? So you have seen that in CNC machines we have stepper motor and servo motors. So what is the difference between the operation of stepper and servo motors? Yeah, you can unmute and answer. What is the difference between a stepper motor and servo motor? Like the basic difference.
Yes, sir. Sir, servo motor is highly precise and
Yeah, I'm not talking
it's
about the precision in.
used in a mod.
Yeah, okay, you're correct. Servo motors are more precise than stepper motors in general. But I'm asking about the operation of the both, how the working principle rather, just the basics of it. Like you don't have to go into depth. But how are they different? Like in stepper motor, we have seen that the rotation of uh, the shaft occurs in steps. So in servo motor, it's continuous rotation based on the input magnetic fields, the sequence of magnetic fields rather. You have a continuous rotation in servo motor, whereas discontinuous or stepped rotation in stepper motor. So from that you have got the name stepper. Yeah, so you're saying that it's option C, that both open loop and closed loop control system. However, in case of stepper motor, we know that whatever signal we give, it will move in multiples of these particular steps, right? So on providing one pulse, it will be moving, say, one or n number of steps, or it can be the other way around. For n number of pulses, it can move by one step. So it depends on how we program it. So the thing here is, in stepper motor, you can't have a closed loop or a feedback control system, because we know that whatever feedback we give, suppose the motor has moved by some point, or say like 0.25 degrees, say that is the minimum step by which it rotates. So once it has rotated by that step, whatever be the error, it can't be rotated by that error amount in the other direction. So that compensation can't be met. So it's no not possible to have a closed loop system there. So we have an open loop control system only. Whereas if we see in case of a servo motor, we can do that compensation. Suppose it has moved by 25.002 degrees, in like that 002 degrees the error, so it can be compensated, and like you can alter the position. Am I clear on this part?
Yes, sir.
Okay, okay. So, coming to the second question, what are the benefits of adaptive control system? It reduces the in-process time, it reduces tool changing time, it improves tool life, it gives reduced operator intervention, and all of this. So, what will be your answer to this? Okay, so don't jump into conclusion by seeing this type of options like all of this and all. Actually, I think if you'll be attending GATE in the upcoming years, then you should be acquainted with multiple option correct type questions. So this is just a basic version of that, but yeah, in adaptive control system, we have seen that it reduces in process time. Yes, by uh, you know uh, implementing a proper control strategy. Suppose a very basic example was discussed in the lecture videos. You have and this type of feature. If you want to generate this type of feature on the workpiece, then suppose you want to remove this part and again remove this part. So you're using a milling tool here. So these particular regions from here to here and from here to here, the tool is not encountering any resistance because it's simply air here. While in this intermediate portions where actual material removal is taking place, it is encountering resistance by the material, and hence we find that the force which is acting on the tool, it's high in like the cutting force will be acting here, while in between where there's no machining occurring, there you have zero cutting force. So in those regions we provide high feed rates here. Feed rate is high in this intermediate portions where you don't have any resistance, because your tool can you know your tool won't be harmed. However, if you provide the same high feed rate while machining, then there are chances that the tool gets damaged. Correct. So that's why we change the feed rates accordingly to improve the productivity. So if you increase the feed rate here, and likewise for n number of such air pockets, you increase the feed rate, and for m number of samples, so you have got a larger reduction in the processing time. So you have got improved productivity. So yeah, it reduces in process time. It reduces tool changing time. See, tool changing is not brought within the domain of this adaptive control system. Like it can be implemented, but generally tool changing, it's not considered under this adaptive control, because adaptive control is implemented only on the machining cycle. So in between, suppose your tool breaks or it needs a regrinding. So that time either it's manually changed, or if there is a turret system, then it's automatically brought. But there the adaptive control system is not playing much of an important role. So this is not a correct option. It improves tool life, yes, by implementing adaptive control system, you can increase or decrease the process parameters like feed rate, depth of cut, based on the uh, process variable values, so say feed force or cutting force. So these are the variables which you can conveniently measure using dynamometers, and accordingly you can modulate the process parameters, which is speed, feed, depth of cut, and other parameters also in other types of machining operations, and thereby you can improve the tool life. Yeah, if you discuss about non-conventional machining, there also say EDM. So if you implement some adaptive control strategy there, so you can also improve the tool life by reducing the tool wear rate. So suppose you have a predefined pulse on and pulse off time. In case of EDM, I am telling. So if you see that, so this pulse off and pulse on time, by these parameters, you define a variable which is called duty factor. It's basically T on, which is the pulse on time divided by T on plus T off. This is the total cycle time. So either by modulating this duty factor, or you can modulate the input voltage or the tool feed rate. So by changing these variables very minutely, you can control the output output responses, which are material removal rate or tool wear rate. So these things, it is possible to do, and nowadays research is going on to capture the in process changes in the output responses. So if you are somehow able to capture the like during the run time of the process, if you are able to capture the output variables, say this MRR tool wear rate, then you can accordingly modify these input parameters and improve, you can change this process parameters so that this MRR and TWR gets optimized. You need to reduce tool wear rate, you need to increase MRR. So these are complementary phenomena. uh, you can optimize these variables by mm, in order to get an optimum MRR and tool wear rate. So again, it improves tool life, yeah, and it reduces operator intervention. Yes, because it is, once it's programmed into the system, you don't need the operator to manually set this particular feed rate or speed in between. Where it can be increased. Say you need to machine this portion of. Suppose you have a grinding wheel, say, okay, you need to grind this portion. So uh, you can set the feed in such a way that in this particular region the feed is less, because there the machining is occurring, while in this portion there is no machining occurring, so you increase the feed rate there. So if you have a manual operator, manual intervention system, then the operator has to come and mm, and change the feed rates. But in case of adaptive control system, that is not required. So you have got reduced operator intervention. So you need to take care that it doesn't do much with the tool changing time. Okay. So coming to the next question, which of the following is not true about adaptive control constraint strategy? So as I already said, that adaptive control system can be realized either in the form of an optimization strategy or with a control constraint strategy. So what will be the answer here? And the controller modulates the parameters on the measured values of based on the measured values of process variables. Uh, you have been asked which is not true. Okay. So first option, we know it's correct because it is common for any adaptive control strategy. That the controller, it changes the parameters based on the measured values of process variables. So how that does, that differentiates the constraint strategy from the optimization strategy. So so here limits are imposed on the process variables. Yes, we have seen that in case of constraint strategy, there are some process variables like the cutting force, as I said. So you have imposed some limits on that cutting force. If the cutting force is beyond a particular value, you won't increase the feed rate. Rather, you can decrease it. if the cutting force is much less than a particular value, then you can increase the feed rate, like in case of the air gaps that we discussed. So first two options are correct with respect to adaptive control constraint strategy. Let's see the third option. An index of performance is defined based on the productivity and tool life, and it is optimized by the controller through modulation of the process parameters. So this is what we have seen in case of adaptive control optimization strategy. So here we have seen that you have some index which is arbitrarily defined. It can be defined as a function of uh, MRR and tool wear rate, or it can be a function of the cost per material removed and the productivity likewise. So such a index is defined, it's predefined, and then your controller is programmed to change the process parameters in order to optimize that particular index of performance. Okay. So this is what we have seen in case of adaptive control optimization, not in case of constraint. So this is the correct option here. It is not true about adaptive control constraint strategy. Is it clear?
Yes, sir. Clear.
Okay. Okay. A couple of questions regarding this adaptive control system only. Yeah. So changing the system parameters by adaptive control system is done by which of the following functions? I hope you have come across these terms, identification function. So as we see that in any adaptive control system, you should have a mm, mm, you should have a system which captures the uh, runtime value of the process parameters. So through some feedback mechanism, it captures the uh, current state of parameters, the current state of process variable. So that is done by the identification function. Then you have a decision function which decides on how to, like, whether to increase or decrease the process parameters based on some already defined program logic. Already, like, it has been programmed into the system. As we said that if the cutting force it increases beyond the given value, then decrease the feed force or the depth of cut set. If if the cutting force reduces beyond a given value, which means that there is no substantial resistance to the tool, then you can suddenly increase the uh, feed force to improve productivity. So sorry, not feed force. You will increase the feed motion, feed velocity. So that will improve the productivity. So yeah, that is done by the decision function. So you have been asked which function changes the system parameter. So based on these two, you know, functions, you have another function which will implement the decision which has been taken, that whether to increase the cutting force, sorry, whether to increase the feed motion velocity or to reduce that. By I'm changing this feed motion and velocity, this is more prominent in case of conventional machining. In case of unconventional machining, you have other process parameters which we already discussed. Like in case of EDM, you have voltage, duty factor, and mm, voltage, duty factor, and feed rate. Similarly, in case of ECM, you have some. If you are having any pump, then the pump speed, then that concentration is already defined. Concentration of the electrolyte is already defined. You have feed force, you have current. So those you can change. So this particular part, that changing the system parameters in order to achieve or realize this decision, and that is done by the modification function. Okay, so the next question, adaptive control can be used when the sources of variability are not many, the process time consumed is less, the production is mass production only, and the sources of variability in the job is significant. So we have seen that it is more beneficial when the sources of variability, which means that your job is having different types of contours, wherein you need to suppose you have a given contour. So it's essential to uh, reduce the production time and also improve the tool life, because your tool is encountering different types of topography during the machining. So also there can be different materials involved. Suppose you are machining a composite material, so you have you can encounter one type of material over here. Suppose, so this circular ones are fibers, and this is matrix. So this is a composite. So suppose you are machining this. So fibers are made of different material than the matrix. So they will impose different resistance to plastic deformation compared to the matrix. As a result, the tool, suppose you have a milling tool here. So when it is encountering the matrix, it is experiencing a particular force. As soon as it is coming in contact with a fiber, say, it is experiencing a higher force. So it will be a dynamic phenomenon. So in such cases, you need to change the feed values accordingly, if required. So this type of adaptive control is more beneficial when the sources of variability in the job is significant. So this was one example where the topography played a crucial role, and this is another example where the material itself is non-homogeneous and you need to machine it. Okay, belt drive can be used for transmitting motion between two shafts which are rotating in the same direction only, which is rotating in opposite directions, either in same direction or in opposite direction or perpendicular to each other. What will be your answer to this? Yeah, rotating either in the same direction or the opposite direction. So, right. So you can check this up. There's one particular arrangement of pulleys where a group from some university, they have tried to rotate two shafts which are perpendicular to each other. But not only with the help of pulleys, uh, I think they use some intermediate mechanism. So you can just check it up if you are interested. But in case of the basic arrangement, as we know, of a belt and pulley, it can be used to rotate the shafts in same direction or in opposite direction. Rotation can be transmitted between two shafts located perpendicular to each other by which type of gear drive, by which type of drive. Spark gear drive, bevel gear drive, belt drive, chain and sprocket drive. Bevel gear, yeah. These are just some basics of theory of machines, what we have already studied in the first or the second year. So this is a bevel gear mechanism. Flat surface can be generated on a lathe machine by holding the workpiece in a 4-jaw chuck. providing cross feed to the tool using a form tool, none of these processes. Yeah, do you have any questions? Sorry. You are not audible. Can you type your doubt in the chat box? Okay, you are answering. Yeah. Yes, yes. By providing cross feed to the tool. So you need to give a feed motion in this direction. So what is this operation called? Facing operation. So when do we use a 4-jaw chuck? I hope you know about.
For proper holding of the workpiece.
So you can also use a 3-jaw
In
chuck,
that,
right? So when specifically do you prefer a 4-jaw chuck? See, 3-jaw chuck can be, they have a self-centering mechanism, so it's always beneficial. But in certain cases, we need to use 4-jaw chuck. When is that? So suppose we have non-uniform. Yeah, tell me. Yeah, what? Your voice is actually breaking. I am not able to hear it properly. See, if your workpiece is completely axisymmetric and uniform, then you can hold it in a 3-jaw chuck, where the yeah, where the heads will properly sit on like their center positions will coincide at a point which will be the center of the which will be on the axis of the particular workpiece. But say you are having a non-uniform body which is not axisymmetric, or it is not cylindrical, say in such cases, when it is not having a properly defined axis, you need to hold it using 4-jaw. So one here, one here. So after turning, you will be getting a circular periphery. I mean a cylindrical surface. But initially it was like this. So to hold this type of workpieces which are not regular and not axisymmetric, we generally use 4-jaw chuck. And these are not having any self-centering mechanism. You have to manually load, like you have to manually adjust each of these grippers in order to grip the workpiece properly. Rotational motion can be converted to intermittent motion by which of the following mechanism? Yeah, Geneva mechanism. I hope you know how it works. You have slots like this. Like it will be properly, cut, not like this. Okay. Then as this rotates, this particular, like the the teeth will mm, cover a path like this, and accordingly it will rotate by one teeth. So that is how Geneva mechanism works. This drawing is not proper. I just tried to demonstrate. So you give a continuous rotation to this particular uh, element here, circular element, and this will be following this in an intermittent motion. So what is the work of rack and pinion mechanism? Like what is it used for? So a pinion is a gear basically, and a rack. This is also a gear, but its radius is infinite. So by rotating the gear, you are converting this rotational motion into a translational motion of this rack. And these are used in lifting robots and all. Worm and worm gear mechanism. What is that? So you have a worm wheel which resembles a screw, and you have another external gear here. The pitch and other factors, like other parameters of the gear tooth, are defined accordingly. And as you give a rotational motion to the worm, each of these teeth in along this pitch, it will push the uh, adjacent teeth on the gear. So as it pushes, this gear will be rotating. Sorry. So this is how rack and the worm and worm wheel works. So just think and tell, if we rotate this particular gear, will it counter rotate this particular worm? Is it possible to get a reverse motion? It's not possible, right? Because yeah, if we try to rotate this, it will be pushing this particular teeth here, but it won't be rotating it. Whereas if we rotate the particular worm wheel, as it is rotating, it will be pushing the gear. So this is the unique property of worm wheel mechanism. It can serve, it can provide high gear ratios, up to 40, 80 like that. But at the same time, the it can be said as an advantage or a disadvantage that you can't